We're going to take a look at being able to take these cylindrical equations and convert them into rectangular equations, so that way it can make it easier for us to be able to sketch the graphs of these. And they do require some sneaky techniques on occasion, which I'm going to show you. So for instance, we have r equals 3. Now r equals 3 is a pretty simplistic equation seemingly, but we need to be able to convert that back into our Cartesian system. So here's what we're going to do. For this one, I'm going to square both sides. And the reason I square both sides is because we know that there's an identity for r squared. Okay, so remember that r squared is x squared plus y squared. All right. And in 2 dimensions, this is a circle that's centered at the origin with a radius of 3. In 3 dimensions, though, that circle becomes a cylinder because the z is a real number. All right? So remember, z is independent. It doesn't necessarily say anything about z. So we actually have a cylinder with radius 3, and the center is at the origin. So if I was to graph that, and it's going to expand upon the z-axis. So let's just assume that this has a radius of 3, and it's just going to keep going up and down on the z-axis. All right, so we should also say it expands on the z-axis, okay, or along the z-axis. Okay. A second example. Again, another sneaky one. Theta is equal to pi 6. Okay. Now, some of you might think about this as a plane, and you'd be correct, because if theta is always equal to pi 6, we don't say anything about z, and we don't say anything about r. So r extends indefinitely, z extends indefinitely. The only thing that we know is that the angle is always pi 6. Here's how we can verify that. What I'm going to do is I'm going to take the tangent of both sides. So tan of theta equals tan of pi 6. And the reason I do that is because in the cylindrical coordinates, remember that the tangent is y over x. Okay. Or we could rewrite tangent of pi 6 as root 3 over 3 or 1 over root 3, right, just by evaluation. We can multiply both sides by x, and y equals 1 over root 3 times x. We know that the z is a real number. Okay? So essentially what we have is we have a line in the xy plane with slope 1 over root 3, centered at the origin, and then it's going to expand upon the z-axis. Right? So now 1 over root 3, if you were to approximate that using your calculator, I think that's like 0.52. So 0.58, I just threw it in my calculator. So we basically have a slope of approximately 0.58 that's going to stem from the origin in the positive direction. So here's what we get with this. Okay. So this is x positive, this is y positive, and obviously z positive. We're going to have a slope in the xy plane of about 0.58. So it's not a 45-degree angle, but it's about a 30-degree angle actually, because we have that pi 6, so we get something like this. Okay, so that's what we have, and then we just construct it, and that's the plane that we get. Right? So notice that this angle right here, theta, is equal to pi 6. So anytime we actually have theta equals a constant, you're going to get a plane that stems from the z-axis. Right? Now, of course, that cuts through the z-axis and it goes indefinitely up and down. It also goes indefinitely the other ways. So, for instance, it just keeps going out this way, keeps going back this way, keeps going down this way, just like every other infinitesimal sort of object that we've seen. A third example, this one's actually fairly easy. We already have r squared, so we can just rewrite this as x squared plus y squared. And then we say plus z squared is equal to 5, just by adding 5 to both sides. And this is really nice because this is exactly the formula for a sphere. The radius is the square root of 5, and the center is at the origin. Right? So if we were to graph this, we just get a regular old sphere at the origin. Square root of 5 is going to be the radius. So we could just say that r is the square root of 5 for this. Right. A little bit more difficult is this animal right here. So we get this r squared cos 2 theta z plus 1. All right, so here's how we're going to try to work with this. We're going to use a trigonometric identity on cos of 2 theta. All right? And there's actually several of these. All right, so you might remember that cos of 2 theta has a trigonometric identity of cos squared theta minus sine squared theta. That's one of the 3 trigonometric identities that it holds. All right. I think there's also one, like maybe 2, or maybe 1 minus a half sine theta, 1 minus a half cos theta, something like that. But this is the one that we're going to utilize, and I'll explain why in a moment. So we're going to rewrite this as r squared times cos square theta minus sine square theta plus z squared, and I'm going to swing that 1 to the other side and make that equal to negative 1. We're going to distribute, so r squared cos square theta minus r squared sine square theta plus z squared is equal to negative 1. And notice right here that r cos theta is going to be equal to x. But since they're both squared, so r squared cos squared is equal to x squared. In a similar fashion, we have r squared sine squared, and that just becomes y squared. And then finally, we can drop down the z squared equals negative 1. Now this is seemingly one of those quadratic surfaces that we looked at in the previous section. The only thing that we'd have to do is multiply by negative 1 to get it all equal to 1. So another way to write this algebraically would be y squared minus x squared minus z squared is equal to 1. All right. Now, what you have to do is you have to go back to that sheet that we have. Okay, and you're going to determine, you're going to look at page 1. It's a type 1 because it's equal to 1. All right, so don't forget about that. And what you're going to do is you're going to look for 2 negative. And I believe if you look for 2 negatives, the only one on page 1 that has all quadratics and 2 negatives is going to be the hyperboloid of 2 sheets. So I'm going to give myself a little more room here to work. So this is going to be a hyperboloid of 2 sheets. Okay. It's at the origin, so I'm going to say the center, and I'm going to put that, it's more like the focal point at the origin. And then we know that it's going to expand on the y-axis, okay, because the y is the only one that's positive. Okay, so I'm going to say it expands on the y-axis. If I were to construct this, and again, I'm not really good at this, so I do apologize, but I'll do my best. So this is y positive, and then y negative. We'd probably get something that looks like this. So we have one of our hyperboloid, and again, this goes out indefinitely. And then we have another one this way. All right. So the one on the right-hand side looks pretty good. The other one's a little bit dilapidated. Sorry. All right. So one last example is we have this r equals 2 sine of theta. All right. This one's another sneaky one. and I'm going to show you the trick. You might remember the trick from Calc 2 when you dealt with polar coordinates. Now, one of the things students like to do is they like to square both sides with this, and that's not a bad idea because you get r squared equals 4 sine square theta. But a better way is to multiply both sides by r, right? And that's going to give you r squared equals 2r sine theta. We don't want to square both sides because sine squared doesn't have an easy translation from cylindrical into Cartesian, but 2r sine theta does. Okay, so r squared, we know our friend r squared is x squared plus y squared, and then 2r sine theta, remember r sine of theta is y. At this point, we're going to subtract 2y, and as you can imagine, we are going to complete the square. It seems like a common technique. That's because it is. All right, so we take half of the middle term. Half of negative 2 is going to be negative 1. Negative 1 squared is positive 1. We're going to factor, just like we have a number of times, and we end up with y minus 1 squared. So this is going to be our equation. Now it doesn't say anything about z, so z is just a real number. It's an independent variable. And essentially what we get is we get a cylinder. Okay, so in 2 dimensions, this would be a circle centered at 0, 1. In 3 dimensions, it's going to be a cylinder centered at 0, 1, 0. Okay, so cylinder center is equal to 0, 1, 0, and the radius of our cylinder is going to be 1. Right? So it's going to expand upon the z-axis. I should say that as well. So I'll say expands on our z-axis. So here's our center, here's our radius of 1, right? And essentially it's just going to kind of conjoin with the z-axis, and we get this sort of shape. We'll try again. If it doesn't work, then that's that. Okay. It'd be a lot easier if it was paper, not a screen. Alright, so hopefully this gives you some of the tips and tricks to be able to convert from cylindrical into Cartesian and then be able to graph. In the next set of videos, we're going to take a look at our second non-Cartesian system, which is going to be our spherical coordinate system.